bring everything to one side. Bring all terms, no.
What if you divide everything?
Hold on a second. I wrote this backwards. Sorry. This is minus and this is plus, right? Yes?
What if you divide everything by xy, sir?
By x,
xy?
xy, well then that would become x squared, but this would be, well sorry, this would become x squared over y, right?
Yeah.
So you can't kill them both at the same time. That's, if you try to divide by x, yes, that'll go down, yes, that'll go down, but then this will have an x under it and that will have an x under it. Okay, let me see here. Does anyone see it yet?
Difference of cubes.
This is a difference of cubes. Isn't that a difference of cubes? And what does a difference of cubes become? That becomes x minus y. Yeah, x squared plus xy plus y squared. So that's our difference of cubes formula on this. Y'all see that? I mean, yes, maybe you have to go look up the formula, but do you trust me that that's it? Yes? Okay, and then that's just this. Then I still have over here, check this out. I'm going to put in parentheses x plus y. I don't need it in x minus y. I don't need it in parentheses, but I'm putting in parentheses on purpose because I want you to see what the next step would be. Yeah, these both have an x minus y in them, don't they? And so I can factor out an x minus y. And then what would you be left with in here? X squared plus xy plus y squared. And then you factored out, right? So you have plus 1 equals 0. And so what could you tell me right now? Like,
X equals y.
that x must equal y. That x must equal y. That for sure, because these two things have to multiply to be 0, don't they? So that would tell me that x must be y. Really what I'm doing is I'm setting x minus y to 0 and then just moving the y over. So the only way that these equations, these things can both be equal to one another, the only way that can happen is if x is y, right? Now we haven't considered this here. We haven't considered this. This is somewhat problematic. Let me ask you something. No, let's not. Let's just go back to this for now. Let's look at this for right now. If x is y, then that means I can come back to these equations and I can just take that y and make it x, right? And I can come back over here and make that y x and then solve those equations. Let's see what we get. So if x must be y, then 4x cubed minus 4y equals 0 turns into 4x cubed plus, minus 4x equals 0. And that we can solve. Just pull a 4x out. We'll be left with x squared minus 1 equals 0. So what do we get there? What are our solutions to that?
1 and negative.
Yeah, 1, negative 1, and 0. We have 3 solutions there. X equals 0, 1, and negative 1. Y'all with me on that? Now, hold on, we're not done. Because if x is 0, then what's y? Well, remember, x has to be y, right? Or y has to be x. So if x is 0, y is 0. That's one critical point. Another critical point is x is 1, but then y has to be 1 also. And then another critical point is that x is negative 1, but y also has to be negative 1. Those are 3 critical numbers, critical points. Y'all with me on that? We have 3 critical points so far. Now, I didn't deal with this here. I'm afraid of where that's going to take us. Because, I mean, technically, this could also be 0 whenever this is true, right? Whenever this is true. So how can we, let me do this. Oh, you know what? The other equation, I erased it. It was this one. I hope that everyone understands on that other equation that if we replace that with x, we get the same exact equation as over there, right? Or if we replace that with y, we get the same equation, we get the same answers for y, and then we go backwards and get x's. So I don't need to worry about that equation anymore, all right? So I'm leaving this right now as an open question. I'm going to revisit it if I have time, all right? That's not going to have a solution, but I want to just put it on the back burner for now. I wonder if there's a way we could have got this without all that, setting them equal to one another. I showed it to you because I wanted you to see that you could do it, all right? But could we have just like started out here, divided by 4 here, get that like that, okay? And then here, this would mean that y is x cubed, right? Wouldn't that? And then couldn't I just come back over here, take that answer, plug it in right there. If I have to satisfy both of these at the same time, replace that y with what? X cubed, so this becomes x cubed minus x equals 0, which is x to what power? 9th power minus x equals 0. Factor an x out, x to the 8th minus 1 equals 0. And now solve that. So what are our solutions there? So 0 there, and then the only way this is true is 1 and negative 1 again. If you do it this way, solving one of these for y, going back in here, replacing, solving, then once we have our x's, then we can get our y's. How do we get our y's? Plug these x's back in right there. So 0 cubed is 0. Negative 1 cubed is negative 1. 1 cubed is 1. So we get the same answers, wouldn't we? I like that way better, because this way didn't have that one piece that I put a question mark on. If we did it the other way, that you would have to deal with that question mark. I don't like that. But like I said, again, I was just trying to be constructive here and show you that you can set them equal to one another. Are we satisfied that those are our critical points? Those are the only ones?
Yeah.
Satisfied? Okay, now what? Well, we have to calculate capital D, don't we? Capital D needs to be calculated, and then we have to look at capital D at every one of these points. So let's start with capital D. What is capital D for us? It's the partial with respect to x twice, which is 12x squared, times the partial with respect to y twice, 12y squared, and then minus the partial with respect to x followed by y, which is negative 4 squared. Now, at each of these points, we calculate capital D. So let's do it this way. D at the point 0, 0. Does that make sense to write it this way? D at the point 0, 0 is going to be what? 0, 0, so 0, and then take away 16. What does that tell us? Saddle point. We should have a saddle point at the origin of this surface. Okay, so this was, x was 0, y was 0, that's 0, take away 16, we have a negative number, right? As soon as we see negative, we know we have saddle. What's D of 1, 1? 1, 1, yeah, so we get 1 here, we get 12, and then 1 there, we get 12, and then minus 16 again, right? And that's positive. I don't care about the value as much, and you shouldn't care either. So we have positive. What does this mean now? If we get positive, that just tells us that we have one or the other, max or min. How do you determine if it's a max or min? You look at this number right here, and you tell me if it's positive or negative. So that's positive, isn't it? That's positive, and positive means that, which means minimum. Okay? We have a local minimum here. And then how about negative 1, negative 1? Same thing. Because it's x squared and y squared, d of negative 1 should give you the exact same result. And also, when you plug negative 1 in here, the result of this is still positive, right? Still 12. So we still have the same thing happening. So local minimum here. Questions? Now, this tells us where these happen, right? But it does not tell us what the values are. This tells me, look, at 0, 0, I've got a saddle. This tells me at 1, 1, I have a local minimum, and at negative 1, 1, I have another local minimum. But what is that minimum? How do we get that? Just plug them into the original function, right? So to figure out this right here, I would like to know what that is as an ordered triple. Like what's the z coordinate here for this point? So just take 1, 1 and plug it in to this. And what would you get if you plug 1 and 1 in there? So you get 1 plus 1 minus 4 plus 1, so negative 1? You get negative 1 there. Understand? And then what if you do this one? Negative 1, plug in, you should get the same thing, right? Negative 1 again. So our local minimum value is negative 1. So what we should see when we graph this is at 2 points we have low points, right? And then in the middle we have some sort of saddle. Or at 0, 0 we have some sort of saddle point. Oops. Here's the graph. That's our surface. Kind of a weird surface, huh? The computer cuts it off, but this continues up almost like parabolically. And so we see our 2 low points, and we found them. Here's 0, 0, 1. That's our saddle point right there. We never computed the z coordinate, right? But it didn't matter because it wasn't a minimum. And then here are our lower points. Okay. How about this one? Do you kind of get an idea of how this is working? Yes? Okay, so let's see if we can't grind through this one a little faster. I don't know. First, I'm going to do all those partials. And do fx, fy, fxx, fyy, fxy. Help me out. What's fx? 3x squared? What? I'm not looking up there. Plus 24x? Everyone agree? Is that right? I don't know. I'm not looking at the function.
Would it be 3x squared y?
3x squared y? Then plus 24x? Everyone agree? Okay. What's f with respect to y? Okay, I'll look. X cubed minus 8. Okay. And then what's fxx? Six xy plus 24. Fyy? Ooh, what's fyy? 0. Nice. What's fxy? 3x squared, that's it. All right, so we need to first find our critical points, which means we need to work with these 2. I'm going to put CP for critical points, all right? I need to know where 3x squared y plus 24x equals 0. And I also need to know where x cubed minus 8 equals 0, right? Those are the things I need to know. The second one is nice, isn't it? That's really nice to see. Because this forces x, doesn't it? This forces x to be 2. There's no way around it. X has to be 2. So in order to make this one true, x must be 2. So right now I know that my critical points all have to look like this. 2 and then something. Understand? Now, if x is 2, then come back over here, replace your x's with 2's, and if you do that, you're going to get 3 times 4, so that's 12y plus 2 plus 48 equals 0. Right? Replacing these with 2's. Because you have no choice, right? To make this true, x has to be 2. And now, solve that. What do you get? Y is negative 4. That's it. There's only one critical point on this entire thing, on this surface. It might be a max, it might be a min, it might be a saddle. Still don't know. But there's only one point to look at. So I just need to calculate capital D. So calculating capital D is 6xy plus 24. That's fxx. Oh, fyy is 0, right? Okay, and then minus 3x squared, but then all of that squared. You don't have to use brackets. You can use parentheses. It doesn't matter. But the book always uses a bracket in the formula, so I'll put it there. All right. What can you tell me right now? You don't even have to compute anything here. Right? If this is 0, right? This is always negative. This is always negative no matter what because you have minus something squared. So this is always negative. So you're going to have 0 and minus a number. So this is going to be negative. So we have a saddle. So this is a saddle point. And if I wanted to have the z value, like if I wanted to know the z coordinate, I could just plug these in to that. And so this surface has no local maximums or minimums. You have no little ant piles or valleys anywhere. We do have a saddle point, though. The algebra on that wasn't too bad, was it? This is pretty clean. Shall we look at it? Oh, wow, what an interesting looking surface. Look at that thing. Our saddle point was right there. You see it? That's our saddle point. It's an odd place to have a saddle point, but that's it. Now we're starting to get somewhere. How about this exponential function of two variables? Okay. Find any local maximums or minimums of this guy. Ooh. What's the partial of f with respect to x? So first of all, you're trying to take derivative of e to something, right? So derivative of that is itself. So e to the 4y minus x squared minus y squared. Oh, shoot. Times, chain rule, the derivative of what's up here with respect to x. Minus 2x, right? Times negative 2x. All right, let me clean that up. That is negative 2x e to the 4 minus x squared minus y squared. We agree? I'm just thinking about how bad these second partials are going to be. Yes? 4y, yes, thank you. I forgot to put the y. I was literally thinking about how bad the second partials are going to be and overlooked that 4 there, or that y. All right, what about partial of f with respect to x? I mean, with respect to y? So what's going to come out in the chain rule this time? We still have this piece, but what comes out after the chain rule here? Yeah, it's going to be 4 minus 2y. So this is going to be 4 minus 2y times e to the 4y minus x squared minus y squared. This is not looking fun, is it? Maybe we should peek real quick at the picture. Ah, it's a pimple. That's it. It's just a pimple. Just one local max is all we're going to get. It's going to be a lot of work to get it, but that's all we're going to wind up with at the end. Jeez. Okay, so now let's hold off on the XXYY for now. Okay? Let's just see if we can get the critical points. So I'm working with this and this right here, and I need to set these guys equal to 0. Well, hold on a second. That's not too bad, right? I mean, if I have to take the first partial, set it to 0, that means all I'm doing is setting negative 2x, e to who cares, right? E to who cares equals 0. We should all know from college algebra, pre-cal, cal 1, cal 2, that e to any power can never be 0, right? So if I set this equal to 0 and I have multiplication here, then the only way this is going to happen is if x is 0, right? That's pretty clean. When I set the other partial equal to 0, same story. We have 4 minus 2y out front times e to a bunch of crap. I don't care about the crap because that's never going to be 0. So that, just set that equal to 0, you get y is equal to 2. Beautiful. So my only critical point is the point 0, 2. So I only need to calculate d one time. The problem is the formula for d requires second partials of this. Okay, well, we're Cal 3 students, right? So we're not afraid of taking second partials. We actually enjoy it, right? fxx. So you got to take the partial of this again with respect to x, which means I have to use what? Product rule. I have a product right there. So I've got to do a product rule there. So the derivative of the first one, which is negative 2 times e. Can I cheat and just go e to that? Is that all right? Okay. And then I'm going to say plus what? Derivative of this, which is itself. Careful now. Times negative 2x again, right? Because you have to go up here and take derivative of what's up there. But then times what?
Oh, the first.
The first one again, negative 2x. So this was like derivative of the first one times the second one plus this, all of this is derivative of the second one, then times the first one again. All right, this is equal to, let's see if I can do this, e to the crap, and then we have negative 2 plus 4x squared. So what did I do there?
Factor out the e.
Yeah, these both had e to the junk or e to the crap in it, right? So we pulled that out, and we were left with the negative 2 here, and then when we put those two together, we got 4x squared. That's not so bad because, you know, I feel like I can work with that. Do you? All right, what about fyy? Similar story, right? Another product rule right there. It's going to kind of follow the same pattern.
It's going to be negative 2. So, yeah.
Negative 2 right here. E to all that stuff again, right?
Times e.
Plus derivative of this, which is e to all that stuff, but with respect to y. So what popped out last time?
4 minus 2y.
Yeah, 4 minus 2y. But then you got to do again times the first one, so it's going to be squared. Which I could have done that here, right? I could have done negative 2x squared once I saw it was twice, but on that one I will. And then I'm going to factor out there an e to the junk again, and then what would be left here?
Negative 2
Yeah, you would have negative 2
times
plus,
or plus.
plus, and then 4 minus 2y squared. So when I pull the e out of this and the e out of that, I'm left with that term, and there they are. All right, I've got to do I've got to do fxy. fxy. So fxy is the derivative of this one with respect to what?
Y.
Y. So the negative 2x is a constant. There's no product rule here now. So I'm going to go negative 2x. And so I'm treating that like a constant. So I'm just ignoring it and I'm bringing it in. But then I take derivative of that with respect to y, which is itself. And then we've done that with respect to y a couple times now, isn't it? 4 minus 2y. Okay. Yeah, it's not too bad, right? We still have to plug in 0, 2 into that after we get d. So d, we'll do d right here. D is going to be equal to this times this minus that squared, right? So this times this, so I have e to that junk times negative 2 plus 4x squared times e to that junk, and then times negative 2 plus 4 minus 2y squared, and then minus, in brackets, negative 2x e to that stuff times 4 minus 2y, but all of that squared. And now we just have to hope for the best that when we plug in 0 for x and 2 for y, that things are okay. So let's talk about this up here. All this crap that we've been ignoring this whole time. What happens when I plug in 0 for x and 2 for y? And that would be into this, right? What happens when I go 2 in for y and 0 in for x? You get 4. Everyone agree? Okay, so when I calculate d at the point 0, 2, I get e to the 4th, that's this, and then 0 is going here, right?
Yes.
So that's just going to be times negative 2. All right, and then times, this is e to the 4th again, and then what's this?
Negative 2, because the inside.
Yeah, this is going to be 2 times 2 is 4, so that's 0 squared, 0. So all we have is negative 2 again. And then we have minus, oh wow, look at this. This one's nice. Because x is 0, right? X is 0 and everything else is dead. So we get this, right? Now, is that positive or negative? It's positive because, these two multiplied are negative. These two multiplied are negative. So put that together, we get a positive. So we have a positive. So we've either got a max or a min here, right? Local max or min. So now what we do is we put all of our attention on this piece right here, that first piece, which is that right there. And that right there is negative. Negative means this, local max. So we have this right here is a local max. And since it's a local max, I'm actually going to find out what the point is exactly. So I'm going to go back to the original function, which is right here. And I'm going to replace x with 0 and y with 2. And when we do that in the original one, we get e to the 4th. I don't know about you, but I mean, when you sit back and think about this now, what you're now able to do, in theory, is someone gives you a surface like this. If I were to have asked you at the beginning of class, hey, look, try and find me like any local highest or lowest points on that, you'd be like, where do I begin, right? This is now a method. We have found that locally the highest point you're ever going to find is this point right here, and so the highest value is e to the 4th. Now, how could you ever have known that that would be the case, right, without this method? Here's the picture. Oh, I already showed you it was the pimple, right? There it is. Okay. What about that one? We've got 10 minutes. Let's see how far we can get with this one. Partial with respect to x. Uh-oh. Okay, let me help out here. Bring this down here. This is the same as x squared plus y squared plus x to the negative 2 times y to the negative 2. I think that's the easiest way to look at that function. Just bring these both up. Okay? I think it'll make your derivative go a little bit better. Understand? Okay, what is our partial with respect to x? 2x plus 0, that's derivative of this, and then here, minus 2x to the negative 3, which will be times y to the negative 2. So we're treating this y like a constant. We're taking the derivative of x to the negative 2. So negative 2 drops out. We subtract 1 from negative 2, we get negative 3. Agree? Now, just for the sake of us knowing what the hell this is 2x minus 2 over x cubed y squared, right? That's what that really is? Okay. Now, what's the partial of f with respect to y? Well, same thing, basically, right? Except we got 2y minus 2 over x squared y cubed. So if you went through and did the same thing, derivative of that would be 2y. This is a constant. Negative 2 comes out. So wouldn't you get the same sort of pattern? Let's do it. What about fxx? Let's go ahead and do this one. So I'm going to do it off of this one. Okay, I'm not going to go back down to this one. I'm going to do it off this one. So derivative of that with respect to x is 2.
6x to the negative 4.
And then plus 6x to the negative 4 times y to the negative 2, right? And then what's partial yy here? 2 should be the same thing. Plus 6x to the negative 2, y to the negative 4. Because it's pretty much the same exact pattern that we had from up on that one. Do you all agree with that? Now this one's going to be a little different. What about partial with respect to x then y?
Be negative.
So that's gone, right? That's 0. And then you're just taking derivative of that with respect to y. So that comes out, hits that negative. So 4. 4.
To the negative third, y to the third.
X to the negative third, y to the negative third. Does everyone follow that? Okay. Now, let's get our critical points. Our critical points, I need my partial of f with respect to x to be 0. So I need 2x minus 2 over x cubed y squared to be 0. I also need my partial of f with respect to y to be 0, which means 2y minus 2 over x squared y cubed must be 0. What to do, what to do? What to do? What do y'all feel like doing with that? I've only got 5-6 minutes left.
You maybe get the same denominator and multiply out both sides by the denominator to cancel it out.
Okay, so let's do this. Let's put these together. This is like this over 1, right? We get a common denominator here. So I need to introduce x cubed y squared on top and bottom. If I do that, I'm going to get 2x to what power? Fourth, y to the second, right? So that's me putting x cubed y squared on top and bottom here. And then minus 2, because I don't put anything on this one. Then I put them all over the common denominator. X cubed y squared equals 0. So I just got a common denominator there. This is going to work very similarly. I'm going to put these together also. Now, in algebra, hopefully you learned that a fraction can only be 0 if the numerator is 0. Essentially, anytime you have a fraction equal to 0, you can just always multiply by the denominator, right? Multiply both sides, and it's going to kill off. So all I really need here is 2x to the 4th, y squared minus 2 must be 0, right? And this one becomes 2y to the 4th x squared minus 2 must be 0.
Wait, x squared or x cubed?
Where? Where?
No, it's x squared. No, sorry.
We're okay?
Yeah.
Y'all follow me? I'm working both of them at the same time. I'm so tempted to just set these equal to each other right now because they both have to be equal to 0. Let's do that. Let's set them equal to one another. 2x to the 4th y squared minus 2 must equal 2y to the 4th x squared minus 2. I think some really nice things are about to happen here. You'll see the 2's are gone, right? Those 2's are gone. In fact, I can divide both sides by 2 now. So I get x to the 4th y squared equals y to the 4th x squared. That good? Very critical step here. Do not divide by y squared and x squared. I mean, people do it. There's a problem with that. And maybe you've seen this, maybe you haven't, but I'll show you real quick. Let's say I have this equation right here. I've seen people do this. I've seen people at this step divide both sides by x. All right? And they get x equals 4, which is true. Okay, so if I erase that, does 4 solve that equation? Yes, so that is a solution. But you're missing one. What solution are you missing? X is 0, right? And that's because when you divide by x, you're making a little promise on the side. You're signing the little waiver without actually signing anything that says, I promise you x can't be 0. So you lose a solution this way. So the way you need to do this instead is how? Does anyone know how you do this instead? Just move everything over to one side. Then you factor out an x. And then you retain both solutions that way. So here, you might be tempted to divide through by x squared and y squared, but then you're making these little promises. So instead, move everything over to one side. Okay, everything's over to one side. And then recognize this can be factored. So now on the left side, I can pull out x squared, y squared. And then what's left inside there? X squared minus y squared equals 0. And so we've got a lot of things going on here, right? We've got x could be 0. We got y could be 0. Or when we do this, be real careful on this one. That's a difference of squares, right? X plus y, x minus y. And when we set each of those equal to 0, we get two answers. X is equal y, or x is equal to negative y. I am 2 minutes running out of time here, all right? Y'all all right with this so far? Okay, now, what was our ultimate goal? Our ultimate goal was to try and solve these two equations, right? Two of my solutions don't work. X can't be 0, right? Because then you have division by 0, here and here. That's impossible to have x being 0. And it makes sense, because x can't even be 0 here, right? The original function, you can't plug 0 in for x or y. So I'm automatically going to chunk these two. They're gone. So the only other thing left now is that either x is y or x is negative y. So let's start with that one. If x is y, we got to come back to the beginning. If x equals y, then what does that equation become? 2x minus 2 over x to the 5th equals 0. You can get a common denominator again, right? 2x to the 6th minus 2 over x to the 5th equals 0. That's common denominator. Kill off the x to the 5th, so this is 2x to the 6th minus 2 equals 0. Move things around. At the end of the day, you get x squared, or x to the 6 is 1. Which means x can be what?
Negative 1 or 1.
1 or negative 1. So you're either going to have 1 or negative 1 for x. Now, what must y be?
Yeah. The same.
The same, 1 and negative 1. So we have 2 critical points, right? Then we have to look at this. What if x is negative y? So do the same thing. What if x is negative y? Or y is negative x? Does it make a difference with this equation? Does this change? If I change this to a negative, does this change?
The first thing on it.
So when you plug in, when you replace, I'm going to do it the other way. If I replace y with negative x, right, that becomes what? Negative x squared, right? Which is still x squared. So this equation is the same. Everything works exactly the same, doesn't it? So what does that mean? That means we're going to still get the same 2 solutions, aren't we? We're going to get 1 and negative 1. But what about the y value? It's the opposite now, right? So it's negative 1 and this is positive 1. You follow that? We have 4 critical numbers, critical points. You have to calculate D on all those, and I don't have time to do that. But here's the picture. They turn this function reminds me of, you know, that little game that you played when you were kids? Maybe you still play it. I don't know. That one where you have the little paper that opens up. It's like, you know, give me a number, and then it's like, you know, what's your favorite color? And you fold, you know what I'm talking about or no? Yeah. That's what this thing reminds me of. I don't know why. You have to flip it over to kind of look at it like that. But there. But this is the function. This is the surface. And y'all can pack up. Don't worry. This is the surface. And what we wind up getting here are four local minimums. Do y'all see them down there? We get 4 local minimums on this surface. So I'll leave that to you. Are we done with this? Nope, there's another one here. And then there's another one. This one I'm gonna offer this as a bonus problem. In your notes, 11.7.9. Now, let me warn you about this. Go ahead and pack up. You can start walking out if you want to. But if you're going to do this as a bonus problem, you need to carefully consider what happens here, because there's something very interesting. And I've given this as a bonus problem, I think, every time I've taught Cal 3. I've only had 1 student in my entire career that has been able to get this completely correct. I've had people get a lot of it correct, but only 1 student's ever got it completely correct. That's because there's something very interesting in here. So, yeah. So I would say if you're going to do it as a bonus, you might want to run it by me first. You know? You might want to just be like, hey, take a look at this. Because your solutions are already here. Okay? I mean, they're here. If you open the notes, you can see the answers. But can you get to those? And there's something missing in the answers. All right, well, that's it, right? See you Wednesday. Have a good one. We're halfway through this section. Sorry for keeping you all over. Ran out of time there.